The idea of this lab is that we're going to build an LRC circuit consisting of this inductor, this resistor, and this capacitor. And we're going to find the conditions under which it resonates so that it produces a strong response to an input signal. And by doing that, we'll be able to determine the unknown inductance of this coil, which when we first built it, we only kind of knew approximately what we would expect its inductance to be. In principle, we could just hook up the oscilloscope's calibration output to this LRC circuit directly, but in reality that's a little risky because we risk blowing the scope by connecting something to ground that's actually at voltage by making a short inadvertently. So because of that, we're actually going to drive this circuit indirectly using this other coil. This is just the one that I happened to have around that I had made, which was 54 turns wound around the end of a Starbucks cup. And so the idea then is that ideally there would be an air gap between those two inductors, and then there would be total electrical isolation between the scope side of the circuit where we're measuring the response and the driving side of the circuit. Now in reality we can't quite get the isolation that good because we need to have the same ground for the return current in the side of the circuit as in this circuit. This is going to be the same ground as one side of the oscilloscope's probe. However, it does make it a lot easier to avoid blowing the circuit if we do this indirect driving of the LRC circuit this way. So this coil, the primary coil, is going to act as an electromagnet. It's going to produce an oscillating magnetic field in this space over here. A changing magnetic field induces a curly electric field, and then that curly electric field is what's going to be picked up by this coil, so it's going to be driving the electrons through this coil. Here's the setup that I came up with in order to get the calibration output from the Hontech scope into my circuit. So this little clip right here is the calibration output, and then unfortunately only a few millimeters away is this other one, which is the ground. And the problem is you don't want to short across these two things. I think that could probably blow the scope. So the way this is designed to be used is that you take the mini grabber of the scope probe and clip it to that, which you can do pretty well without risking shorting across here. However, we need the mini grabber in this experiment to hook into the actual receiving circuit, so we can't do that. So this is what I came up with. This right here is a paper clip that I had, and it's a paper clip that has plastic insulation. I think you can probably see the plastic insulation. It's a little bit white on there. So that ended up being pretty convenient for me. The wire strippers worked well for me for getting the insulation off of this end, and also getting some of the insulation off of this end. So I made a little tiny hook, stuck it through there. Then I took my stylish plaid duct tape. I put a first layer under there to cover up all of these logic connectors that we're not using in our course. Then I stuck the paper clip in, which has insulation on there anyway, but I figured it wouldn't hurt to cover up the logic connectors. Then I put a second layer of duct tape on top just to hold the paper clip in place. And that way I have a nice safe way to connect onto the signal output of the scope using an alligator clip without risking shorting this out. So, for instance, I could have just taken this alligator clip and tried to clip it on directly right there. I was really worried that if I did that, I was going to inadvertently short out these two connectors. And by the way, I did all this with the scope plugged into the computer, so it was under power, but you'd probably be smarter to disconnect the USB connector so that if you do inadvertently touch something up there like a screwdriver while you're trying to set this up, you won't be actually shorting the scope. So here I've got my partially complete driving circuit going from the calibration output of the scope through a 47 ohm resistor to limit the current, and then through the coil. The idea of the resistor here is that we want to make sure that we don't get too much current flowing through this circuit. Without the resistor, we'd only have the impedance of the coil. And then I have this problem where I need to get a complete circuit. To complete the circuit, I need to get back to the ground of the whole thing, which is basically the USB ground. So we have various places where we have access to the USB ground that we need to get back to complete our circuit, but they're not super convenient, most of them. Up here, the top one of these two connectors is a ground, but I don't want to try to connect onto that to make a second connection. That's already scary enough in terms of shorting out the scope. On channel 1 and channel 2, the inputs of the scope, we have these BNC connectors, and the outer conductor on those is supposed to be a grounded connector, and in this scope it is connected to the USB ground. But I don't have any easy way to connect onto that. So what I have ended up doing is just connecting the probe onto the channel 1 input, and then here I have the ground clip connected onto the probe, and I'm going to use that ground clip as a current carrying connection into my driving circuit. And this is not generally something that I would want to do. I'd rather not use this thing, which is supposed to be just a signal input, as a current carrying connection. But because of the current limiting resistor, the current flowing through this is actually pretty small, maybe 50 milliamps or something, and so I think it's actually okay to connect this. So here's our completed driving circuit. We've got a complete circuit going from the calibration output of the scope through the 47 ohm resistor to limit the amount of current, through the coil, and back to ground through that alligator clip. And I want to watch out here, like if this alligator clip were to touch that one, then we'd be shorting across the resistor, and then probably a large amount of current would flow through the output of the scope, limited only by the impedance of the coil, which is not that much. So for that reason, I'm going to take some Scotch tape and just tape this down to my desk in place, and that way that can't happen. So here's my completed circuit. The primary or transmitting coil is my 54 turn coil that I made before with regular insulated wire. The secondary or receiving coil is this 200 turn coil that I made with magnet wire. So here's the primary circuit, which I showed you before. There's my resistor that controls how much current can go through the primary coil. And in the receiving circuit, I have the coil, another 47 ohm resistor, and this capacitor, which right now is a 47 nanofarad capacitor. So it's an LRC circuit. This is what's known in the trade as a rat's nest. I use Scotch tape to hold some things down so they wouldn't move around. And I want to point out how the scope is connected in, because this is important if you don't want to blow your scope. So there are two connections to the scope. That's because the scope is a voltmeter, so it basically wants to measure a voltage difference between 2 points. This is the mini grabber, which is going to one side of that blue resistor. And then I have the ground clip on the scope right here, which is going over to there, and that's connected in to both the primary circuit and the secondary circuit. That's undesirable. I would have rather had no connection at all between the two circuits to avoid possible shorts, but I need a way for the current to return back to the computer's USB ground in the primary circuit. And in the secondary circuit, the scope needs two connections into the circuit so it can measure a voltage difference between 2 points. So that's why I need to connect to the scope's ground in both the primary circuit and the secondary circuit. So in the secondary circuit, I'm connected to the two sides of the resistor. That means the scope is measuring the voltage difference across the resistor. And then through Ohm's law, we can connect that to the current, which is flowing in this side of the circuit, in the secondary circuit. So the ground is connected in there. If you trace that through this black wire, which is the ground clip, and then through this red wire. Then the ground is also connected into the primary circuit because the black wire, which is the ground clip coming from the scope, is going to this white wire. And so current is flowing back through that side of the circuit to the ground side of the scope. So now that the circuit's hooked up, let's go ahead and look at the measurement on the scope. You can see it's a little bit messy, but we're getting a clear response on the scope. I can make sure that is a real effect by changing the distance between the primary and the secondary. So if I do this, it goes away. So that's a real thing. It's a little messy. There's some kind of higher frequency logic signal superimposed on top there. Maybe if I freeze this for a second, you can see that better. So you can see that there are these little steps and spikes. Those are not the signal we care about. What we are interested in about is the lower frequency thing that looks more like a sine wave. So the output directly out of the oscilloscope's calibration output would be a square wave with this frequency of 20 kilohertz, which I guess you can't read because it's too bright. And so that would look like this: square, 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 square. But what happens is the LRC circuit filters that. So that square wave can be analyzed as a superposition of sine waves, and the lowest frequency one of those sine waves, the fundamental, is the one that's at 20 kilohertz, and our LRC circuit is tuned in to that resonance. Since the other frequencies that are present in that sine wave are way outside the resonance of our LRC circuit, they get filtered out. So that's why this looks more like a sine wave and not like a square wave. The signal on the scope is a little messy, so it doesn't trigger cleanly. If we were to try to measure that the usual way on a scope, it would be hard to get good quantitative data. Actually, the software gives you a nice feature for that. If I zoom in here on the bottom of the screen, I think you can see there's a bunch of text down here, but it's too crowded together to see. To make that visible, I grew the window, and now I think you can see that there were separate text fields here, and the one that I found useful was this one that says millivolts with a tilde after it, meaning millivolts AC. This is some kind of measure of amplitude, and it does seem to properly reflect the amplitude of the signal on the scope, and it's a pretty convenient way of getting a number. Now I want to show you that this thing really is resonating at a certain frequency. So the easiest way to do that is to change the capacitor and verify that we can get off of resonance and the circuit will stop responding to the signal. So a simple way to do that is to take a second capacitor And in principle, this is what I actually tried at first. I can just go like this, touch those wires to the alligator clips, and if I can make good electrical contact, those capacitances add in parallel, and then I should get a different capacitance. In practice, I found that did not make a reliable enough connection to be usable. So instead, I put together this little thing, which is a second capacitor with banana plug leads hanging off of it, and that way I can make a better, more reliable connection onto the circuit. So I have a 47 nanofarad capacitor already in the circuit, and now I'm going to add a 33 nanofarad capacitor into the circuit in parallel. So that will almost double the capacitance of the circuit. And now when I put in the second capacitor, I think you can see a pretty dramatic reduction in the response on the scope. So here is with the correct capacitance, which is closer to 47 nanofarads. And now here it is with the wrong capacitance, which is almost twice as big as it should be. And it pretty dramatically filters it out. Low response, high response.